I guess I put on the screen the wrong set. We still have a couple of slides to finish from last time's. Any questions before we proceed? Okay, let me go back to the comparison of sensitivity. So we have discussed those different flavors of sensitivity calculation, and I want to finish by talking about the differences between them when it comes to accuracy, consistency, computer effort, and human effort. But I realized that maybe you are not aware of why this topic is important. That is, I told you that I've invested a big chunk of my professional effort over the years in method for calculating sensitivity. Dr. Kim has a book on the topic. Why, when you do structural optimization, do you think sensitivity takes such a central place? Why is sensitivity one of the most important topics in a course on structural optimization? When I do a course on optimization in general, I spend almost no time on how to calculate derivatives, but when it comes to structural optimization, depending on who is teaching the course, it could take as much as 40% of the class time to maybe I'm doing maybe 20%, but it's one of the major topics. Why?
Because to calculate objective whatever constraint or function it takes, it is very expensive in mostly structural optimization. Like if we have to calculate a finite element and do a finite element analysis for calculating the sensitivity or something like that.
But that's true for almost any discipline. You know, people who do CFD spend even more time in the cost of simulation. They have a few papers on derivative calculations, but hardly as much as we do. I mean, your answer, Satish, is partly correct, but I want to look at it from the most general. That is, we don't do it in optimization. We do it in structural optimization, and it's more pronounced in structures than in other disciplines. So my question is basically two sides. Why, when we teach optimization, we usually don't bother with the question, and why, when we do structural optimization, it becomes very important. And the other part is why structures more than CFD, let's say. So let's first focus on the first one. If you think about it, you have courses on optimization which has to do with optimization algorithm, and almost against my will I teach here some optimization algorithms. That is, people who take such a course often don't have another course in general optimization, and if they had another course in general optimization, they didn't maybe cover all the optimization algorithm, but things like genetic algorithm and particle swarm optimization, there is nothing special that ties them to structures. So you could take them in any general optimization course. Then you can take a course on finite elements. And so you could say, you take a course on finite element, you take a course on optimization, and then when you need them, you just connect, tell the optimizer, f min con, to call the finite element analysis, and if that's complicated because of the computer language, then you work on some kind of an interface that would allow you to do that. So as Atif said, this is usually infeasible. It's too expensive. So the place where we establish our presence as structural optimizer is how to allow this connection between optimization and finite element analysis. On the one hand, people that do finite elements are not particularly experts in derivative calculations because for a finite element analysis they typically don't need it. People that do optimization don't know much about structures, so they cannot take advantage of the shortcuts that are available. So you can think of this segment of the course as what are the shortcuts that are available to structural optimizers in order to do derivatives in ways that are either cheap, accurate, requires very little effort, so that depending on how expensive is the application and how much time you have, you can decide how much special knowledge of structures you are going to use. Now, if we ask the second question, why is it more prominent in structural optimization than people that do CFD type optimization? Anybody? I think that I answered that question some time ago, so maybe you remember or maybe you can figure it on the spot. What is the basic difference between the solution strategy of the discretized equation, normally between structural analysis, finite element analysis, and CFD analysis? Does anybody know that? Again, I mentioned that some time ago.
Is it about Eulerian or Lagrangian?
I'm sorry?
Is it about Eulerian or Lagrangian?
No, this is nonlinear. No, I mean, what you are saying, Oscar, is correct. In structural analysis, we typically describe things in Lagrangian reference and in CFD in Eulerian reference, but it doesn't have to do with the computational shortcut that is available in structures and is not available in CFD. And that has to do with the basic solution. That is, if you get 1 million equations of structural finite elements, you will use a certain solution strategy. If you get 1 million equation in CFD, you will use a different one. That will change the equation, but I'm talking about the solution method. You have 1 million linear equation in one case and 1 million linear equation in the other. A CFD person will solve them differently. That is, this is after you have done the discretization and you just have a bunch of numbers on the computer representing the matrix on the right-hand side. Given the matrix on the right-hand side, a CFD person will use a different solution strategy than a structures person. Anybody? Well, I mean, there are not that many available, and you know what structures people use, so even if you don't have any idea about CFD, you can possibly guess. What do we use in structural analysis to solve the finite element equations? What solution method? Just a set of linear equations, only that it's large. Yeah, that is, you use a variant of Gaussian elimination. In CFD, you don't do that. What do you use instead? I mean, there are some people that use finite element CFD and then do it anyhow, but it's very rare. Most people don't. So if you have a large system of linear equations and you don't use Gaussian elimination, what do you use instead?
Thomas algorithm.
Sorry?
There's other types of Thomas algorithm.
Thomas algorithm. I'm not sure. What kind of algorithm it is?
How you decompose?
No, you don't. Decomposition is inherently Gaussian elimination. So CFD people don't use Gaussian elimination. The reason that they don't use Gaussian elimination is because their matrix is not positive definite, so you cannot do Gaussian elimination without pivoting, and pivoting will destroy the sparseness, so that you have million equations with million unknowns, you'll end up with a decomposed matrix that will be a million by a million, which is a lot of computational work and a lot of storage. So they don't do that. How can you solve a system of equations without doing any Gaussian elimination? Well, all the basic methods are iterative. You may remember Jacobi and Gauss-Seidel. Those are primitive ones. There are accelerated methods that have some conditioning. There is conjugate gradient, but they all have the same principle. You try something and then you gradually iterate. And the advantages of all of those methods is that you don't need to change the matrix, so you don't create non-zeros from zeros. But the disadvantage is that every time you change something, you have to go through the process all over again. There is not that gain that you get from Gaussian elimination, that you invest a lot of effort on decomposing the matrix, and then if you change the right-hand side, it's a small investment. So this is one of the main reasons why we have all kinds of shortcuts in structural analysis. Okay, so just wanted to make sure that you didn't lose sight of the big picture. And we talked about those different variants, all of these different variants except for finite difference derivatives normally try to take advantage of one way or another. So, yes?
I think I still got in a good appreciation of the reason we're doing this sensitivity analysis. For example, in our homework, we found the derivative of the tip displacement with respect to the length.
Mm-hmm.
So what would be the benefit of this, for instance?
Okay, so you design, let's say, an airplane, and you want to design it so that the tip of the wing doesn't hit the runway when it lands. So you have a constraint and f-min-con will want to calculate the derivative of that constraint so that it will know how to change the design without violating it. If you call f-min-con without telling it that you are going to give it a subroutine with the derivative of the constraint, it will go ahead and calculate it by finite differences. And if that's affordable, then you sort of forget about derivative calculation. F-min-con does it for you using finite differences. If, on the other hand, you find that, like Satish said, every time you want to calculate the tip displacement, it takes you several hours to do that, and you have 10 design variables, every time f-min-con calls for derivative of the constraints, you're going to wait for a day for one iteration of f-min-con, and you look for some method to provide a shortcut. So derivatives are needed in order to do optimization using all the derivative-based methods that we studied, like sequential quadratic programming, which is what f-min-con uses, generalized gradient approach, which is what Excel uses, sequential linear programming, most penalty function techniques that convert the problem to an unconstrained problem and then use things like conjugate gradients. augmented Lagrangian, feasible directions. All of those are methods that need derivatives. So you can always do finite differences, and if you are willing to spend enough computer time, you can make it as accurate as you want, and you can make it as consistent as you want, so that if the cost of calculating derivative by finite difference is not an issue, and that will happen to you a lot when you do simple problems. And fortunately, in engineering, you often run into simple problems. Not everything has to be modeled with a million finite elements, so that's perfectly okay. Discrete derivatives, which is what you'll find typically coded in to finite element codes, and it doesn't matter whether you do them by finite differences, that is semi-analytical or computational, will be consistent. That is, when you change your finite element model without changing the number of elements, the derivative will predict what will happen to the stress. If, on the other hand, you do remeshing, then this consistency is not that important. There is not much difference between the accuracy of continuum and discrete derivative, but if you have noise factors like remeshing, continuum derivatives are more important. So when you look at the type of problems that people solve, for problems that involve changing sizes only, they are sometimes called sizing problem, like designing the cross-sectional areas of trusses or beams, or the thicknesses of plates or shells, people will overwhelmingly use discrete derivatives. When you come to shape optimization, where every time you change the design, you may want to change the number of finite elements, then continuum derivatives begin to appear more frequently. Still, even for shape optimization, the commercial codes use discrete derivatives, and this is because it's much easier to program. Computational cost. So this is where we have the edge over people that do finite elements and people that do optimization. Continuum and discrete derivatives are cheap because of the fact that we take advantage of this Gaussian elimination. It doesn't matter whether it's continuum or whether it's discrete, we still do that. Computational derivative, on the other hand, where you just take your computer program and you call for ADI4 or ADOL-C to differentiate it for you, will be expensive. Could anybody tell me why? Well, the first reason I already told you about, without substantial human intervention, they will not be able to take advantage of the fact that you already decomposed the matrix. And so that's why people have this hybrid that I mentioned last time, where they use discrete derivatives, but they calculate decay dx with computational differentiation. That is, they use the compiler just to calculate decay dx. But there is another reason, and the reason is that those programs are blind and they sort of calculate the derivatives of every line on your computer program, whether you need it or not. So it's sometimes difficult to tell it to be frugal. Finite difference derivative are expensive. If you have 1,000 variables, and for each variable you do a new analysis, then calculating derivatives will cost you 1,000 times more than a single analysis. I mentioned an exception. Does anybody remember What was the exception? This was nonlinear structural analysis, where the analysis is expensive, but the sensitivity is linear, and you can do a Newton calculation at the very end, do one additional Newton iteration and get the sensitivity. So, and this was the thing about CFD. Occasionally you have iterative solution of structural equations. People that do finite element modeling of nuclear reactors, whether it's the structure or they sometimes use finite element to model the nuclear reactions, not only the structure, sometimes avoid Gaussian elimination. Can anybody think about the difference between airplanes and nuclear reactors? That in terms of, think about the geometry that may favor Gaussian elimination for airplanes and cars, let's say, but not for nuclear reactors. If you were under great security restriction, so that you'll need to describe to somebody the kind of structure that a nuclear reactor is without saying that it's a nuclear reactor. But if you think about, in terms of two structures, let's talk, for example, the containment structure of a nuclear reactor versus, well, to make it easy for you, compared to this room. Okay, that is, civil engineers usually use finite elements. So if they had to model this building, they'll use finite element and they will use Gaussian elimination. People that do nuclear reactor may not. Can you think of any inherent difference between the two buildings? What do you expect would be, if you think about some ratios, what ratio do you expect will be substantially different between a normal building and a nuclear containment? Yeah, that is, nuclear reactors are not thin wall structures. Now, why is that important for Gaussian elimination? Does anybody see a connection? When you have a plate, even if you use solid elements, the bandwidth tend to be small because it's in the plane. So if you have something that looks like that, you may have 1,000 by 100 by 5. Let's say that we are doing temperature analysis or only 1 degree of freedom. You have 500,000 equations, and if you have a temperature here, it's connected to, 1 to 1,000, 1,001. Well, it will actually go 5,000 depth, so this would be 5,001. So the bandwidth would be 5,000. If, on the other hand, you have something which is more like a nuclear reactor, which is for the same 500,000, you may have here maybe 500 by 200, no, let's say 200 by 200 by 12. Now the bandwidth, no, that's still, difference is too big. Let's make this 10 so that I'll have 1,000,000. And then I have 100 by 100, we get much coarser discretization, and we get a larger share of the bandwidth, and when we decompose the matrix, it fills in much more. So occasionally you have problems for which it's too expensive even to do Gaussian elimination, and people that do nuclear reactor occasionally resort to conjugate gradients to solve their problem. So they become a bit more like CFD people. So this is the computational cost. And finally, implementation effort. So the main point that I want to get here, global finite difference is cheap. And don't let all the papers that are published about other methods make you forget that. That is, in most applications, that's what you'll be using. Unfortunately, what happens is that people find that it's too expensive, and they find ways of improving global finite differences by using approximation, and that becomes a problem. You can find off-the-shelf discrete and semi-analytical approach, so this requires very little. And computational derivative effort is very problem-dependent. There are some programs that you can just give them to Adol C, and you'll get a C code with the derivative built in, and you just run it and it will do. And there are problems that you can spend a year just finding out all the bugs that has to do with the special features that you built into your computer program. Any questions? So here is the kind of question that I want you particularly to ask. And this is like the question that Saad asked at the beginning: why do we want derivatives in the first place? So things about the big picture. What is, the message that I try to get across is that depending on your application and depending on the availability of code, you may use one of those different options. Is there any application that you are considering that you are doing derivatives that it's not clear to you at this point what derivatives you should be using? Okay. So let's go to eigenvalues. Eigenvalues are particularly attractive because of these shortcuts that we have. In a perfect world, I won't need to do bullet number 1, which is to remind you about the properties of vibration modes and buckling modes. You are all specialized in structures, and so you probably had it in one place or another, but I'm not going to take chances, and I'm going to do that. And then I'm going to press with the point, if there is one application in structural design where you can get derivative cheaply, those are derivatives of vibration frequencies and buckling loads. So whatever you do when it comes to vibration frequencies, this is the place to be tempted the most, but into not using finite differences. That is these are so cheap that it's staggering. Furthermore, those derivatives, the formula that you use is very easy to understand physically, and if you understand it, it tells you how to change the structure even if you don't know anything about optimization. And finally, we will talk about sensitivity of eigenvectors, which are derivative of vibration modes. Could anybody think of any situation where we will want to change a vibration mode? Remember, Saad asked, why do we want derivatives? We want derivatives so that we will know how to change something by changing the structure. So when would we want to change the vibration mode of a structure? Or in your case, Satish, the buckling mode of a structure. Not the buckling load, not the vibration frequency, but the mode. Let me give you a clue to one very important application, and this is car designers put in a lot of effort to make sure that the important vibration modes of a car have a desired shape.
In order to avoid resonance?
No, avoiding resonance depends on the frequency, not on the mode shape.
What's the difference on the cars? The impact?
No, let's just talk about vibration. Vibration is unpleasant in a car, and so, I am driving an old car, and so it begins to vibrate, in my case, 61 or 62 miles per hour is a resonance frequency for that old car. So this is unpleasant, but beside the frequency, there are other aspects that depends on the mode that will make it more or less unpleasant. That is, right now, the biggest unpleasantness that I have is the noise. My keys start chattering, the door, start rattling. What aspect of the vibration modes come in that I may not like? Given the fact that, unfortunately, I hit a resonance, why would anybody care about what's the mode of that resonance?
Frequency, the frequency of the car is close to the nature of frequencies.
Well, this is frequency, but again, I'm talking about, so think about the fact, did anybody recently ride in the back seat of a car for a long period of time? No. Okay, that's too bad, because this is the way to find out. Oh, you did. Okay, as compared to riding in the front seat, is there a disadvantage for a long trip in particular that you can think of? I'm sorry, space. You didn't experience, for example, increased motion sickness type feeling, or turns out that this is the same in airplanes. If there is turbulence, then people who sit at the back suffer more than people who sit in the front. And a clever airplane designer will make sure that that happens, because the people who sit in the front typically pay more than the people who sit in the back. And in the case of a car, it's even more apparent. The people who bought the car very rarely sit in the back. And in general, the front seat is much more utilized than the back seat. And so if you are to suffer a vibration mode, you don't want the peak amplitude to be at the driver's seat. And there are maybe other places where it's also sensitive. So mode shaping is important. So now that I gave you a concrete example, can you think of other fields where mode shaping may be important? When you have measurement devices, whether you carry them on a spacecraft or whether you carry them in any place else, you either find what the vibration modes are and put that sensor at the place that would be most stable, or you will, if you have to put it in a particular place, you'll try to change the vibration mode so that it's not going to rattle this instrument a lot. So, for example, satellites that takes picture, the place that you want to rattle the list is where the camera is. Okay, so just so that you know why we bother to calculate derivatives of eigenvalues. And now for a few equations. To make for commonality between vibration and buckling, I'm writing the eigenvalue problem as k minus mu mu equal to 0. K is the stiffness matrix, and for vibration m is the mass matrix. For buckling, m would be the geometric stiffness matrix. If you didn't take a finite element course where you learned about those quantities, just take my word for it, that this is the standard way to calculate either vibration frequencies, and then mu will be the square of the vibration frequency, or buckling loads, and then mu will be the amplitude of the buckling load. And this is called a generalized eigenvalue problem. And we have also a normalizing condition that says the eigenvalue has to have a magnitude, and you often specify the magnitude versus the weight matrix U transpose WU equal to 1. Could anybody tell me why we need this condition? Usually when you learn about solving vibration problems, you just see this equation. So if somebody asks you to calculate a vibration mode, that vector u, why is this equation by itself not enough? If you think about it, for u, it's a homogeneous system, right? You have k minus mu m times u is equal to 0. And a homogeneous system either have the trivial solution, which is u equal to 0, which will be the case outside resonance. And when mu is equal to one of the eigenvalues, or one of the vibration frequency, the matrix becomes singular, and the solution is no longer unique. That is, if a certain shape is a vibration mode, 7 times that shape is also the vibration mode. So you typically have some normalization condition, and it's either in this form or you say the largest component of that eigenvector is 1. These are the two most common. could anybody tell me what are the properties of the mass and stiffness and mass matrix that you recall from any course that you took in finite element or vibration course? They are special matrices. They are not, they have some favorable properties.
Symmetry, positive.
Okay, so K and M are symmetric. M and K are positive semi-definite. For sure, most problems M is positive definite, while K could be positive semi-definite if rigid body motion are allowed. So if you are doing this for a spacecraft, then K will be singular. And as a result of those properties, the geometric stiffness matrix, on the other hand, is not positive definite. And that reflects the fact that sometimes you can have a structure buckle under compressive load, and sometimes you can have the same structure buckle under tensile loads. That is, you can change the sense of the loads, and the structure will still buckle. And the reason is that, you can have loads where some panels in the structure are in tension and some are in compression. So for example, if you have a beam and you apply this kind of a load, think about it as a wing. So for load in this direction, the lower skin of that beam will buckle, and for load in the other direction, the upper skin will buckle. And so mu could be either positive or negative. For vibration mode, we know that we will have only positive mu's because they are the square of the frequencies. So these are special properties. Does anybody know what special properties the eigenvector have? That is the vibration modes or vibration frequencies, or buckling modes. Orthogonal, that's correct, but not exactly. What do you mean by orthogonal?
To each other.
No, but for example, if we have buckling mode U1 and buckling mode U2, it's not true that U1 dot U2 is going to be 0. What is true? In what sense are they orthogonal? The dot product is not 0.
With respect to the matrix.
Yeah, which matrix here?
M.
Right. So U transpose M, U1 transpose MU2 will be 0. That is, and furthermore, and this is a very important property, there will be, for every eigenvalue, there would be an eigenvector. There are no vibration frequencies that don't have vibration modes. That may sound like a strange assertion, I mean, something which is obvious, but if you have non-symmetric matrices, for example, you can have eigenvalues that are sort of deficient. There are not enough eigenmodes. That is, you can have fewer eigenmodes than eigenfrequencies, eigenvalues. Now let's look at the differentiation. What I did is I simply differentiated the equation, the eigenvalue equation, and k minus mu m times u has this term. From differentiating that part, we got this term, and then we differentiate the matrices and put it on the right. We can similarly differentiate the normalization condition, but to calculate the mu dx, which is the derivative of the square of the frequency with respect to x, we just pre-multiply this by U transpose. That is, we take the vibration mode, pre-multiply that, and because k minus mu m is symmetric, this term will be 0. And so you'll just be left with this. And so this is a very simple recipe for calculating the derivative of the eigenvalue or the derivative of the square of the vibration frequency. It just says U transpose times dk dx minus mu dm dx divided by U transpose mu, which is usually 1. So first of all, I want to establish that it's extremely cheap. That is, after you have calculated the vibration mode, you know U. Unlike linear response, you don't need to solve a new system of equation with a pseudo-load. You just take the vibration mode and multiply it by these derivatives. Normally, when you change a little part of the structure, dk dx and dm dx would be very few terms. And so this is dirt cheap. On the other hand, compared to linear response, the cost of vibration calculation is more expensive. So doing the vibration analysis is more expensive than doing linear analysis, but the derivatives are cheaper. So relatively speaking, doing derivative of vibration frequencies by finite differences is not smart. In linear structural analysis, the relative gain is smaller. That is, you can essentially calculate thousands and thousands of derivatives for the cost of a single analysis. Furthermore, there is a physical meaning. If you look at U transpose dk dx U, could anybody give me a physical meaning of that term? Let me give you a clue. Let's say that we make dx finite, that is, we change the structure a little bit. And so instead of dk dx, let's just have a delta k. U transpose delta k U. Could anybody tell me what would that be?
Change in strain energy.
Yeah, it's essentially what we called compliance before. It's the change in strain energy due to x. So if this is big, the derivative is big. If this is small, the derivative is small. So if you are going to take the cantilever beam that you keep analyzing, and you may be sick of that beam, if we want to change a little part of that beam, that is, make it stiffer, for example, thicker, or change the Young modulus, or change the volume fraction, so that we will get big benefit from this term, where on the beam we should change it. That is, when I say where, think of the beam as having places on the beam having two attributes. We have the fixed end and the free end, and we have top or bottom or middle. So top and bottom are certainly better than changing the middle. What about tip and root, or free end and clamped end? Which elements in the beam contain more strain energy?
The one closer to the root.
Root. Right. So if you want to increase the vibration frequency of a beam by making it stiffer, do it at the root and far from the neutral axis. The other term is mu times dm dx, and u transpose dm dx u, or delta m. What does that measure? This is a bit less apparent, but think about the fact that we are doing harmonic motion. It's kinetic energy. That is, what we'll have here is omega square delta m, and u times omega is really the velocity. That is, u dot is omega u, and so it's the kinetic energy. So if we now want to reduce the frequency of a beam by hanging weights on it, where should we hang the weights? At the tip, right? Because this is the place where we will impart the maximum. And every few years I read a paper where somebody invents a method to redesign structure from physical principle in essentially coming up with this type of equation that you get by just differentiating the vibration frequencies, because it's so appealing. So what I hope that I convey to you here is that this is the wonderful thing about derivatives of vibration frequencies. They are cheap, and even if you don't calculate them, just by looking at the structure, you can tell how to change it in order to change the frequencies most efficiently. So you completely satisfy the Coiter paradigm. Before you calculate the derivative, you know which derivatives are going to be large and which derivatives are going to be small. Any questions? Okay, that will be all.